But then he was playing soccer, which is a long time tradition in that program, collided with somebody else and broke his collarbone, which forced him, there was sort of nothing left to do then, but like struggle with the problems, and he realized how interesting it was. And I'm pretty sure that I was, since I was the head counselor at that program at the time, that I was the person who sat in the hospital emergency room waiting him for his collarbone finally to be set, which would then project his future course to a national. I know it's a bit of a stretch. So anyway, but his talk today is, and now I can't remember because it's not the same as the last talk I saw. Math is not a spectator sport. All right, thank you.
I hope I'm doing the right things with this. Looks like maybe some light will come out of it. But I can chat for a bit until hopefully something appears on the screen. So anyhow, thanks for the lovely introduction, and thank you indeed for driving me to the hospital. I think if you hadn't done that part, then none of this. But I would still be lying on the field. You couldn't drive that. Maybe you accompanied. Yes, thank you so much. I do appreciate it. And I want to add a footnote to something that Tom said earlier. He mentioned Math Fest in Hartford at the end of July. And at the museum, at the Math Museum, we are, I don't know, I guess you don't keep chalk in these places. Oh wait, here's a yellow piece of chalk. All right, the lone piece of chalk. So from August, following right on the heels of Math Fest, August 4, 5, and 6, the museum is hosting its first math conference at the museum, and also at the Baruch College. Thank you, it's more visible. Also at the Baruch College Conference Center. So our conference is called Moves, it is a conference on recreational mathematics. So over the years, there have been a couple of conferences. Richard Guy organized one in Calgary in the 80s, and Ellen Burlekamp organized one at MSRI or at Berkeley in the 90s. So we figure it's time now, another decade or two has passed, to have another conference on recreational mathematics. It's easy to remember from the name MOVE, that is the mathematics of various entertaining subjects. So we hope to see you all attending our conference in New York City, August 4, 5, and 6. I hope you can make it. All right, so let me launch into math is not a spectator sport. And if math is not a spectator sport, then obviously you'll be participating, which makes me your coach, which of course means that I need to be wearing a t-shirt, not this thing here. And speaking of Tom's story, some of you will recognize this as the, the characteristic t-shirt of that program in Ohio that he was referring to shortly ago. All right, so let's get right down to it. As I said, math's not a spectator sport, so I hope you all brought pen and pencil or paper and pencil and so on, because I have a problem for you. You have to do a problem. What is the slope of the line between minus dd squared and 0, cd, where c and d are arbitrary positive numbers? Now this one's good because even if you forgot your pencil and paper, it might be simple enough for you to do it in your head. So I'll give you just a second, because you should do it, right? What did I say? Math is not a spectator sport. You've got to get involved. Okay, so this is the hard part when you're up in the room to actually. Don't call out. I want everybody to be able to come to this on his or her own. This is the hard part where I have to actually be quiet and let you do something for me. It's the hardest thing to do up in the front of a room, is to stop talking. But here I go. Okay, you guys look like you're totally on top of this. So it's not too bad. We just take the difference of the second coordinates and divide it into the first coordinates, and we get c minus d. All right, terrific. So I've got another one for you. Here we go. So what is the slope of the line between 0, cd and c, c squared, where c and d are arbitrary positive numbers? I'm not going to give you as much time this time. Okay, so hopefully you brushed up on the last problem. Okay, and sure enough, Just take c squared minus 2d divided by c, and it's again c minus d. Great, terrific, you're all excited, right? So what have we done? So that's the question. What have we just accomplished? Now this is where I will be happy to take some participation. Please explain what wonderful thing, which by the way, many research mathematicians who stopped at the museum are not aware of. What wonderful thing have we just shown? So I want to explain in English, or at least mathematical English, what it is that we just did in the last 4 slides. It can be summed up rather neatly. We multiplied 2 numbers, but how did we multiply those 2 numbers? All right, well, so this is the point. It's very difficult to develop mathematical intuition purely from symbol pushing, right? Certainly insight with symbol pushing, and certainly symbol pushing is an extremely powerful method because we almost effortlessly proved what was somehow discovered another way, which is that any chord of a parabola that passes through the axis of the parabola at the product of its 2 x-coordinates. Right? That's what we showed. Take any parabola, take any 2 points on it, take the chord. That line passes through the axis at a distance from the vertex equal to the product of the 2 horizontal displacements to the side of that axis. And we have an exhibit built in the museum, a physical thing where you can see this happening. So we've got this. We had to use a parabola because we needed room for all of these chords. But every central cross section, this is just a parabola, and we've provided chords from between every pair of integer radii, in this case for the paraboloid, and all these lines pass through the central axis. And for example, I should have a laser pointer, but here's radius 1, 2, 3. For example, this is the chord between radius 2 and radius 3 crosses the central axis. You can almost read that right at 6. And so on and so on. And people come and they discover this property, and they look at the property and they say, hey, look, oh, that's lovely, thank you so much. And they say, hey, look, 7, there's no chord passing through 7, so you're starting discussions of primality and compositeness, and it's a great laboratory for seeing what's going on and developing mathematical intuition. So that's what we try to do at the museum. We try to create laboratories where people can immerse themselves in the mathematics in a direct, experiential way, and hopefully get some of the insight and intuition that lies behind the symbol pushing. So here's the museum. This is what it looks like on the outside. And since you've all been kind enough to listen to me for a few minutes this afternoon, I'll let you know some of the, at least one little inside tidbit that most people just walk right by without ever noticing. And it's right here on the facade of the museum. You see there's sort of a shelf along here, and it runs actually all the way around the facade of the museum. In fact, it even runs on the inside of the museum, right above where those letters MOMATH are. And what is going on in that shelf? Well, it's inlaid with brass. Here's a sort of long view of that shelf, and you can see its patterns. There's a lot of patterns in the museum. And in fact, if you take, if you were to take a close look, then you would see, silly computer. You would see that actually the shape of these tiles, maybe a little hard to see from where you are, the shape of these tiles up here, because obviously this is the tessellation, the tiles fit together, and they cover the whole surface, yes, thank you, with no gaps or overlaps. But the shape of these tiles is different than the shape of the tiles right here. They're actually slowly morphing over the course of the entire surround of the museum. It's what's called a parquet deformation, where one tessellation is transformed continuously into another. It was designed by Craig Kaplan at the University of Waterloo, who is one of the leading experts on parquet deformations. Okay, so don't walk right by. When you do come to the museum, please take a moment to appreciate his fine work. You also might bump into Mo Rocca. Sorry, I just had to throw that in. Okay, and this is what it looks like when you come into the museum, and we've tried to make it a visual feast as well as hopefully a great opportunity for exploring things. And look at all these wonderful exhibits we have. I do have to say, and the reason I have to say this is because this picture here actually serves to sort of introduce two exhibits in one. This is our Math Square, our interactive, it's actually the world's only in-ground video display multi-touch screen. So the screen actually knows where each of the people on it are, and this is filling in the Voronoi regions. If you know what those are, I'm not going to take the time to describe what they are, filling in the Voronoi regions of all the people that it's detected. But you can also see there's this rather incredible moire. Those lines don't actually exist when you go and see it in person. They are an artifact of the interaction between the refresh of all those LEDs on the floor and the CCD of the camera that took the picture. And we have a whole other exhibit called Pattern Mesh, which is entirely about moires, which is not pictured here, except you can see that moires still do play a role in our lives even now. So, anyhow, there you go. These are all these great things in the museum. And I want to call attention just to two of them in particular. This is called the Math Annum, and it's a sculpture studio. You start with, say, one of the 5 platonic solids, and you've got a host of operations that you can do to it, such as truncation, cutting off the corners, or elevation, which is to add a vertex to the center of your face and pull it out or push it in. Snubbing, if you know what that is. Again, I won't go into this. The simple operations are actually called the Conway operations, after John Conway, from which you can make a huge host of beautiful creations. And if you play with it for a while, you're virtually guaranteed that you've created a polyhedron, that nobody else has ever created. So there's new math to be discovered, and we can all do it. That's another one of our big thrusts at the museum. And here's another one. So rather than just simply have people put sliders for the 4 parameters of a tree fractal, what are those 4 parameters? Well, they have natural interpretations in the human body. There's one angle for how in your case, that'd be the left branches branch out, and there's another angle for the angle at which the right branches branch out, and there's a length scaling factor of how do the left branches scale compared to the length of the trunk, and there's a right scaling factor. So it's much, you get a much more of a sense of what's going on by doing this than you do by taking little sliders that say, angle 1, angle 2, scaling factor 1, scaling factor 2. So we put people, and then of course you want to put the people's picture into the fractal. You can see as they move, these people's images are being replicated to form those 2 fractals. And there's a very simple reason for that, which is that people like to look at themselves. Well, I brought some museum with me. So we're going to play now and hopefully develop some feel and some intuition and some direct enjoyment of some cool things. So let's see. You are going to be working together. I know that that's maybe just current doctrine, but it does work well, for at least especially for the first activity that we're doing. So what I need is a couple of volunteers to come on down and help me distribute, because having the experience involves lots of stuff, and so there's lots of stuff to go. So there's probably, given the size of the audience, enough for everybody to have his or her own pair of scissors. So if you can...
Have you all signed your insurance?
Yeah, exactly. That's right. I hope so. I think that's it from this bag. Oh, that's very good.
My God.
Yes. And let's see. So what's next?
Should everybody take one or just in pairs?
Everybody should take... Well, I think there's enough scissors for everybody. So if there's enough scissors for everybody... Okay, so what we need now... I'm now going to actually demonstrate while those are going around. You need to be in groups of 4 for this activity. Okay, so groups of 4. And we're going to have... Yeah, so a little self-assembly would be great. So I'm going to have... what's your name? Brian. I'm going to have Brian come around, and I'll probably go around myself, actually. And you're going to get this lovely plastic ribbon. And whoever in the group of 4 has the greatest arm span is going to do this, and then somebody in the group is going to snip at that point. And we need 1 piece of ribbon per group of 4. Okay, so if you want to grab a roll, and I'll start where I know there are scissors. So look, you guys look like just a natural-born group. So I think you've got the biggest piece. Just go ahead and reach that right out. Well, you do have your leg. Okay, then someone's got a snip right there. That's good. So then, just snip right there, and then keep that piece of ribbon. And I will move on. All right. So no one else over here. Okay. Right. Well, you can get by with 3, and then what's going to happen is you're going to come down to the front. Right. Okay. So that's the penalty for 3, is that you come on down and help me demonstrate. Okay. All right. Wonderful. So get your piece of tape here.
Yes, I didn't realize you were such a valuable commodity. Oh my God.
All right. You guys should do. There you go. Okay, very good. Excellent.
So you are
Wider. So you're like before. So here we go. And you guys look like you're We're short. You're short. You've only 2 of you, huh? Okay. Well, you need to unify. I see some. Union. I see communities being created. It's a great.
I think you're the best.
And who's got the largest arm span here? You do? Okay, excellent. All those other great things about you that we have to hear about, and the greatest arm span. It's almost too much stuff. Yeah, but not his hand. Yeah, right, okay, very good, excellent. All right, how are we doing? All right. Excellent. Okay.
Simply connected.
Is there any group without?
Not simply connected.
All right, excellent. We made excellent time. So, there's a group of 3 who's going to come down and be my guinea pigs here. So come on down. Now you have 4. So did we come out to be a multiple of 4? Wow, that's not possible. Okay, so I do need what? You don't have a group. Excellent. Here's a group, and you guys have tape. Brian's not the longest arm span. Sorry, I hate to break it. Keith is not the longest. Yeah, I'm so sorry.
Brian has the longest.
Brian does, not Keith. Yes, exactly. All right, we're good to go. All right, and so now what you're all going to do. So I'm these guys' coach. All right, and in every group, one of you needs to be elected coach. Because the initial part is only involved 3, but don't worry, coaches. You're going to have a very critical role at the end of this activity. So not all is lost. So elect a coach in your group, and I'm your guys' coach, and coaches just take after me. The first thing, coaches, you should instruct your team to do is to tie a knot between the 2 ends of the ribbon so as to make it into a loop. All right, so that's the key first thing. So go ahead. All right, exactly. You want to use up as little of the ribbon as possible to leave it, nice big, for a nice big loop. Yeah, you're cool. Okay, so I'm assuming that by now you have a loop. And now we want the 3 team members to take their most dexterous hand. That is the hand that's most like their right hand. If you listen to the Latin. We were talking about Latin earlier, but in any case, your best hand, Greek, is that Greek? Excuse me, sorry. Okay, so Greek. So in any case, your best hand, 1 hand from each person, and each of you use one of those hands to make the loop into an equilateral triangle. Okay, so you might have to stand up. All right, excellent. A very fine equilateral triangle. Good. All right. So now, all right. Now, coach coaches, because your team may have a tough time looking up here. Teams can try to look up here, especially coaches look up here, and watch what's going to happen. You're going to take your lousy hand, or lousier hand, and... No, you need to hold... Oh, you are right-handed. Oh, okay, fine. So you were holding with the wrong hand for demonstration purposes. I appreciate your nobility. So, okay, so you're going to take your lousy hand, which in my case would be a left hand, and you're going to clasp around both leads coming away from your good hand. Okay, so you're going to make sort of like a little loop there at the end of your corner. And now you're going to slide your bad hand in toward the center of the triangle so that all 6 segments you form are roughly the same length. And so coaches, this is where you really come into play. No, that's 3 segments. You should have 6 segments. A central triangle and 3 leads. Yes, that one looks beautiful. That one's lovely. So coaches, help your team judge when all 6 segments are the same length, because that's critical. Keep your forehand in a nice little K symbol, looping around your there you go. Okay, so no, central triangle. So this should be equilateral triangle with 3 segments off of it, and they're all the same length. Okay. All right. Very good. Okay. Now, I don't know about you guys, but when I used to be in class, I used to try to sit there and say, all right, where the heck is the teacher going with this? So some of you may have guessed where we're going to go with this. All 3 of the good hands are now going to rise up on the same half plane created by the equilateral triangle and meet above the centroid. We'll call it above. Meet in the projection of the centroid of that equilateral triangle. And what have you made? You made a regular tetrahedron, platonic solid number 1 for the day. Okay? Excellent. So, great job, teams. Great job, coaches. I see a lot of... No, you're not done. You're not done. I see a lot of beautiful regular tetrahedra out there. All right, now, here's the tricky bit, especially because since I didn't give you yards and yards of tape, the surface is now rather small. We're going to convert this. We're going to do something with this. So you all have your good hand at, I will call it the apex, and you may want to actually now orient it so that that equilateral triangle is parallel with the floor, and you really are holding your good hands at the apex. Now, this is something that you have to listen to before you do it. Okay? So don't try to start until I've said the whole thing, and maybe don't even try to start even after I've said the whole thing until you've thought about it for a minute. Here's what's going to happen. Make sure, let's just do it this way. Make sure that the only thing sort of in the loop at the apex is your thumb. So stick your thumb in that loop and leave all 4 of your other fingers free, pointing up in the air. Now, you're going to take your index finger, but now, don't do this until I've described the whole thing. Don't any of you do it until I've described the whole thing. You're going to take your index finger. Now, around the person's thumb, the person who is counterclockwise. Counterclockwise as viewed from above. Right? One of the people is counterclockwise from you as viewed from above. Okay? And that person has around his or her thumb a loop of ribbon. That loop of ribbon has the side that's closer to you. It then goes over the thumb and the side that's farther from you. You are going to take, and all 3 of you can do this more or less simultaneously, you're going to take your index finger and you are going to capture just the side of the ribbon that is closer to you, leaving the other side. Yes, coaches, excellent. There's great coaching going on right here. Leaving the other piece of ribbon free. Okay? So you want to reach out with your index finger. You leave your thumb hooked into your piece, but you're reaching out with your index finger to grab just one side, the near side of the next ribbon over, and then you're going to make that OK symbol linking them. Okay? Any questions before we do this? Okay. I'm going to repeat that by showing down here, if you can see it, and coaches especially look. I'm going to pretend all of a sudden that I'm you have it a little bit okay, anyhow, here, I've now become Okay, very good. You're going to go stand over here. Okay. All right, now we're in good shape here. So we see we have these all joined at the apex. I'm now going to take this index finger and grab just this ribbon. Simultaneously, all those other ribbons are going to be grabbed, and we're going to make our OK symbols. So we're now each holding 2 ribbons at the top. And coincidentally enough, if you look at the bottom, we're also holding 2 ribbons down there. Okay, that's what you want to do. Now I'm going to pre-stage what happens next. We're going to gently slide out from the center on top, loosening things up until we have an equilateral triangle on top as well, and produce this lovely shape. So now you guys can all go ahead and do this. And you get a nice equilateral triangle on top. And I'll come around and see how things are going. So you need to go a little bit. Yeah, there we go. Just go. Yeah, good job. Yeah, This is great. Look, you guys are great. This is the best audience ever. Yes, you guys know your platonic self. You've already developed some intuition, and hopefully you're developing more. Yeah, you just want to relax a little up top. I mean, and then let get the slack from the bottom as it evens out. All right, that's really good. Okay, I see an extremely fine collection of equilateral triangular antiprisms, also known as regular octahedra, but we sort of went by the antiprism route. That's kind of was the inspiration how we got there. Okay, super. So that's 2 platonic solids. Should we go for 3? Yeah. Well, that's an exercise for the reader later on. Okay. So this is where the coach comes in, because your team can't do it alone. All right? We're going to convert this cube into... Sorry, we're going to convert this octahedron into a cube. And here is how we do it. And I'm going to do it from below, so hopefully the coaches will be able to see. So hold it up as high as you can. Oh, hey, look at that. You guys are great. So... yeah, they're dual. That's interesting, isn't it? Okay, so what do we have to do? So at a cube, in a case of a cube, we're going to have 3. Right now we've got 4 faces meeting at a vertex. We only have 3 faces meeting at a vertex. That means I got to kind of gather up 3 ribbons. So I want to make all these things into squares. So I got to add another side to this. Another side to that, another side to that. Don't let go of anything. Yes, very important. Team, don't let go. Okay? So I'm going to kind of grab these and pinch them together. And I'm going to take an opposite face of the octahedron and grab these and pinch them together. And now we're all going to just jimmy around and relax. You got to relax. You got to let it and give us some slack. And lo and behold, and you two, Brian, keep that stretch out away from each other. Whoops, you got to keep your fingers together, but you guys got to get farther apart, and I got to get farther apart from you. There we go. So you can certainly convince yourself that at least combinatorially, this is a cube. It's all square faces. But no, you're good. It's all you can get. You don't have to limit it. You got this hand should be a little higher. Yep, there we go. Okay. So there we go. There's our cube. So all you have to do, coaches, is pinch. Let's do that again. For a lot of people, when I do this activity, it's it's really just kind of getting familiar with what these shapes are. That a triangular pyramid, if the base happens to be equilateral, and if you raise it up just the correct height, you get all 4 identical faces. That's a regular tetrahedron. And that the identification between a regular octahedron and a equilateral triangular antiprism. And for everybody, it's a real surprise, when that cube comes out of nowhere. But, and at this kind of an audience, we can ask ourselves, what relationships among these graphs allowed us to make those transitions? Is it a coincidence? Is it a surprise that it was such a simple step to go from the octahedron to the cube? Does it have something to do with the fact that they're duals, or did we use that fact or not? So I will leave you to ponder those things. Unless you think this is all child's play, here is, and restaging what Tom had said, here's your exercise, here's your homework. What operations would take you on from here to a dodecahedron if we wanted to continue our march? Or is the dodecahedron the right place to go next? Should we go to an icosahedron, and how many people will you need? Is another fun question. And how long a piece of ribbon will you need to do that? So I will leave you to ponder all those things, but I hope you get a sense that actually getting down and dirty and involved, brings up questions and it illuminates some of the aspects of what's going on here. So if you guys have time, and if you would like to, we can do one more laboratory exercise, shall we say. Would you like that? All right, delve in. And so there is really no better piece of mathematical equipment than a sock. So you could please distribute socks over on this side. One sock per customer. That's all you really need. And here, if you could distribute some socks down here, and we won't use all the socks, but I'll throw 3 bags. Just for the sake of, I see, I got a wide receiver out here. This is really taking this now. There you go. Excellent. Okay. Now, no, please stop. Okay. So, all right. So, I think in the interest of time, I will cut to the chase, so to speak. What I would like you to do is, can somebody throw me a sock? There we go, thank you. Okay, so this is a tube sock. That's no accident. I don't like this ugly mismatching gray piece. So what you need to do, are there any scissors? Don't throw me scissors. What I want you to do, yes, believe it or not, is I just want you to snip that right off the end. We don't need no stupid gray piece at the end of our sock. And I think you probably can guess where I'm going with this. I'm going to want you to feed this end into that end. And for today's activity, we need to attach those ends. You can see where we're going with this. You guys, yes, are going to make your very own cotton torus, which really should be in every well-appointed mathematician's top drawer. You never know when you're going to need a cotton torus. So, but we do need to make we do need to attach it here at the end. So you feed some in, so there's some access there. That'll be handy. But you need to attach it here. And for that purpose, I have various things. I have cloth tape and I have safety pins. Yeah, just a little bit in, not all the way around, just a little bit in to attach it to make a torus. So, what? I wouldn't. I mean, that'll complicate the points that I'm about to make. You obviously, if you're feeling bored at this moment, go ahead and try for the Mobius thing. So I'm going to pass around. I'm going to start passing around various safety pins and or cloth tape. You feel free to use whichever you think is going to work the best to keep your torus, well, toroidal, I guess, is really the point, isn't it? So the cloth tape works in that sort of funny way. You take a piece of it, you cut it off, you stick the sticky side down, then you take the paper off and you stick the other side. It's double-sided tape if you want to try double-sided tape. I'm just going to seed the audience here with, let me start over there, I don't want them to feel left out. Here's some safety pins. Here's some cloth tapes, if that were whichever you can hold out. If you think that one is better than the other. I couldn't decide, so I will leave it to your, just when I go in the back here, I don't want them to feel left out. But now we got this. Oh, the unity's been broken, I see. That's sad. But this is an individual activity. So here's some cloth tape. See if that'll hold your tori together. A little torus medicine. And do I have anything else? I do have some more cloth tape over here, so that you can get the show on the road. And you may want to use those scissors. Everybody has scissors, right? you may want to use those scissors to cut the clock tape and so on. Okay, very good. So I'm gonna, yeah, while you guys are very nice, I like that. I will say, some of you may know George Hart, who was with the museum for a while. He's a wonderful mathematical sculptor, and he did say that he had never done a public presentation of any physical mathematical equipment without at least at one point over the course of the presentation that thing being built going on someone's head. And here we are, true to form, so we're very thankful for fulfilling that quota, as it were. Okay, and you know, white is so suggestive, right? I mean, really, we can't let these socks stay white, can we? So I'm gonna just distribute. You're gonna need some markers. I'm gonna just be distributing markers while you guys are getting your tori all affixed. And so hopefully here's a couple of markers for you guys. You're going to have to share, but I figured we've already been through all these trials and tribulations as a team, so sharing shouldn't be too difficult at this point, I hope. There's a bunch of you right here, so I'll give you, I'm just avoiding yellow and, I'm avoiding yellow and orange, I'm afraid they don't show up very well. So here you go. You guys can share those. Okay, excellent. Okay, and you guys. Yeah, cough it up. Okay, here's some things, some markers for you guys to share. Do you guys have markers? Yeah, you guys have markers back there. So definitely be generous with your friends. Make sure they get. There's 3 of you back here, and I've got 3 markers for you, so you're all going to share.
I was led to believe this is double-sided.
It is double-sided.
Well, then why can't I get it right?
That I don't know. Okay, you're going to have to come down and share the marker. Okay. All right. Okay. So here's some markers, and share what to say back here. The socks are yours to keep. Courtesy of the moment.
I'll take one just
Marcus here, we're going to be using these in a minute. Yeah, them on here and there. Excellent. Here we go. Here's some, there's roughly 3 of you here. So here's roughly 3 markers. Okay, and there's roughly 3 of you here. And so, let's see what I've got. I'm slowly running out. I think I'll get to it. Okay, so. No. Well, you can do whatever you like. I haven't suggested a particular thing to color yet. These are for you all to share. I will make some suggestions as to a good thing to color. But if you want to write your name and personalize your Taurus, go ahead. Feel free. I have no beef with that. Did you make a movie as Taurus? Oh, yeah. That tape is good stuff, isn't it? Yeah, that'll fix you up. That's the tape that harried executives carry in a briefcase for if their pants rip open just before they go on stage for a big presentation. And no, I didn't use any today, just in case you're wondering. Okay, yes, you guys definitely need some markers. I can see that in your eyes. You have like green and brown. I hope you like those colors. All right, excellent. And a bunch here. There's 5 of you, and I have 5 markers left. So, yes, exactly. So you guys all should figure out how to share these markers. I'm going to drop one of them. I'm not going to resume. The markers I would like back, actually, to tell the truth. Okay. And it's definitely the scissors, but don't throw them. Okay, so there's 5 of you, there's 5 markers. You're in shape. Okay, so what we're going to do, now you all have tori, and I hope they're reasonably well sealed up. I have a nascent Taurus myself. I did, yes, I had a nascent Taurus myself. Okay, so what we want to explore in the brief few minutes left to us is we want to look for interesting circles, interesting loops on our Taurus. Yeah, some of you figured that already. Okay, that's fine. So, I mean, what kinds of circles are there on the Taurus? And what do I mean by what kind of circle? I mean, look, we must be doing topology, right? If we've got this floppy piece of cloth in a torus, it's screaming out topology. So we don't really care about where things are. We feel like we can slide them everywhere they're around as long as they don't break or tear anything. And we can, stretch and squeeze this surface wherever we want. And so we're looking for different kinds of circles. When you allow this kind of sliding and squeezing and stretching, is there only one kind of circle on here, or is there more than one kind of circle? Yeah. Yeah, there's just a little local circle, right? So I have some markers left for myself. So there's like a little local circle. And the little local circle, oops, my torus can't park because I didn't take time to seal it. So the little local circle, you can just draw a little circle right here, just like that. And okay, that's fine, and you can slide that anywhere, that's perfectly loop. You can shrink that down to a point even, right? You can kind of slurp that all into one point. Are there any other kinds of circles that you can find on a torus? Yeah, right. We can kind of imagine you were Magellan and you happen to live on Toro world instead of Earth. You can do the Magellan thing and you can go for a ride all the way around. And when you do this, and I do recommend you do at least one of these all the way around the world circles. And when you do this, make it really nice and heavy. We want to make sure we're able to see where that circle goes through all of the shenanigans to follow. Okay, so I'm going to go all the way around here, and I recommend you do that all the way around. If you prefer, some people are smart, I think they prefer to go around the inside of this curve. But anyhow, one that does a equatorial dance around the entire torus. Okay. If you don't want it on your pants, then do it on the seat next to you, and the stores will clean it up. I mean, UConn will clean it up for you, I'm sure. Okay, very good. All right, so there we go. I've got a circle. So now we've seen two different kinds of circles, a little local circle and this big equatorial circle. Is there can we promote this guy to the head of the class? He's found a different kind of circle, but the one thing he didn't do because he jumped ahead is he did not get my very strong advice to make that circle a different color. Right, so everybody sees there's this one that goes all the way around. There's also one that grabs the ring, right? That's another kind of circle, right? One that grabs the ring. And I strongly recommend that you make the ring-grabbing circle a different color from the sort of equatorial Magellan-type circle. And of course, they will have to intersect, I believe. I think that's right. They have to intersect somewhere, so don't worry about that. And again, make that really nice and heavy. As you go around, really pound that ink into the sock as you go around there. And so you can see very clearly your two different kinds of circles, which we're going to call Magellan circles and ring-grabbing circles. Okay? If you wanted to hold this torus without it slipping away, right? If you hold by a ring-grabbing circle, the torus can't slip away, right? Okay, so that's why we have those two names, Magellan and ring grabber. Okay, so there's two different kinds of circles there. Excellent. All right, so you should eventually end up with something that looks roughly like this, although you must have nice, deeper, brighter colors than I do because I didn't hand out any yellow or orange. Okay, super. So now, here's the question. Here's my question for you. Are those really different kinds of circles? Is there anything topologically we can do? Whereas by topologically I mean, imagine stretching the sock, shifting around. I can twist. Like, remember I said there's smart alecky people that like to have that equatorial circle on the inside? Well, it turns out I'm one of those smart alecky people. Look, I put my orange circle on the inside, not the outside. So there's no difference between this inside the circle and this outside the circle because I can do a topological thing. I can twist and shove and stretch and so on to transform between those two things. Or if I want, I can twist it so it's like on the top. It's neither around the middle or around the outside. So I can make those transformations. Is there a way of twisting, turning, changing the shape of this thing to turn a ring-grabbing circle into a Magellan circle or vice versa? Yeah?
Do I have to stay where I am? Do I have to stay where I am?
Stay where you are?
Can I go inside the sock?
Inside the sock. So very interesting. So again, in the interest of time, we're now going to do something that is decisively not topological. However, I'm going to try to convince you at the end that it was inessentially so, and we can get rid of this. So I want you to take those lovely sharp scissors that we've all been making jokes about, and I want you to just cut a slit. You know the old saying, I slit a torus I slit, and upon the slitted torus I sit. So here we go. I want you to make a slit in your torus. Well, whatever way you like the slit to go. I made my slit like a little, hello there, I am your friendly neighborhood torus. But, you know, it's up to you how you really would like to slit it. You can slit it in the other direction, works as well. And once you've slit it, you should be able to pull all fuzzy sides out. So you see it had a nice smooth side you've been dealing with. But if you cut a slit, you should begin to be able to pull fuzziness out from your torus. Okay, so things are going to get very fuzzy on the outside. And I want you to make all the smooth go away so that only fuzziness remains on the outside. Okay? And when you do this, you will get something that looks a bit like a sausage. Because all of math is really a bit like making sausage. You may have noticed that.
Like legislation.
Like legislation, right? Exactly. It only becomes elegant at the end. And this is a great disservice that the writers of mathematics do to the students of mathematics. They make everything look like it was, you know, all in a beautiful natural pattern and preordained from the very beginning. And they hide all the messes that they made while they were discovering the mathematics. And so one of the things we're going to do at the museum is to celebrate that messy process of discovery. So here we go. Here's our mathematical sausage. And you should get something that looks like this. And now we're imagining here that we've sewed this up again. And now, what topological shape is this? It's still a torus. Of course it's still a torus. Just now you can see the hole, the donut hole, is kind of a longer tube. It goes down to the middle there. And this is, you know, this is now the ring of the torus around this way. So it's a very fat, tall torus with a very thin hole going all the way down the center. Now, if all has gone well, and if you followed my suggestion to write very heavily with your marker, you should be able to see your two lines through the sock. I can see my yellow and orange. You can probably maybe even just barely make out my yellow and orange. And now I would like you to remember what color you had grabbing the ring and what color you had making Magellan. And at least for me, I now have a yellow. This direction around here is now the Magellan direction, right? Because if I grab this, I can pull the torus right out. So the yellow is now a Magellan circle, whereas the orange is now the ring grabber. If I put my finger around that orange path, then sure enough, I am sticking, and I'm going to actually, my finger is actually going to appear here in just 1 second. There it is. There's my finger. I'm actually grabbing that whole torus around the orange ring, and there's no way I could possibly pull that off. So you see, in fact, the Magellan circles and the ring grabbing, the Magellan circles and the ring grabbing circles really are equivalent. Now you will say, wait a second, Mr. Whitney, you just pulled a fast one on this. I saw you cut that torus. So, you know, let me try to convince you that that doesn't really matter. And I'm going to do that in two ways. One is, if you think about how do you make a torus, I'm missing the white chalk because I'm bad at it. It's up front. Thank you. How do you make a torus? Well, you start with a square, right? You start with a square, and you say, okay, here's a square, and you say, okay, I'm going to glue this edge to that edge, in the same way that'll make sort of a tube, and then I'm going to glue this edge to this edge, and if you think about it, in this case, the Magellan circle comes from a line like that, and the ring grabbing circle comes from a line like that, but this piece of paper can't possibly know whether it was, you know, this way on the blackboard or this way on the blackboard before you started identifying things. So those two circles have to be the same by symmetry. There's no way they could really be any different. And you say, but still you cheated. You cut a hole in the torus. And so now I have some pictures. Oh, look, there's the torus with the two kinds of rings. Excellent. Some pictures to try to convince you that that really isn't important. Because remember, the essence of topology is not tearing or disconnecting. But nobody said there was any problem with part of your surface penetrating through another part of your surface. Nobody said that they had to always avoid each other. They just had to remain continuous and connected up in the right way. And so here's two different pictures of a torus in the middle of being turned inside out, of course passing through itself. It does have to pass through itself to be turned inside out. You sort of, you just, you leave it all connected. You can't do it with actual cotton. Cotton is a problem because of the Pauli exclusion principle. But you just shove some of it. You just shove some of that cotton through the other. You shove some of the torus through the thing, and you get a little lump of inside of torus here, and that comes out and grows, and you get these two sort of inversions that end up, going around the torus, and these are going to eventually cancel out at the other end, and it will be turned inside out. Or if you don't like that, just think about in 4 dimensions, it wouldn't matter. I wouldn't have to cut this hole, right? Because I could just reach, I could displace this part of the torus a little bit in the 4th dimension. I wouldn't be pulling it through. I would be missing, because I'd be in a different 3 space than this part of the torus is, and I would just pull it through in 4 dimensions, no problem. So I really didn't cheat. That was really, the whole point of the scissors was to get around that stupid Pauli thing, and we've shown that in fact, although the fundamental group of a torus is the free abelian group on 2 generators, the 2 generators are completely equivalent. I mean, it has to be, it's free. The 2 generators, we just shown the 2 generators are completely equivalent. And that's all I have for you today. Thank you so much.